We're going to be discussing Newton's universal law of gravitation. Now, I think the Apple story is a little bit of a myth, but what the Apple story is telling us is that Newton was the first, at least recorded, to put together the concepts of objects falling towards the Earth and the concept of objects orbiting each other, like the Moon orbiting the Earth, Earth orbiting the Sun, etc. And that was a rather extraordinary notion at the time. These two concepts were sort of understood, but the fact that they were linked together and caused by the same thing was unheard of. So, that force that we're talking about here is that force due to gravity. Now, just as a bit of a reminder, in year 11 you talked about the fundamental forces, and we had the strong and weak nuclear forces, we had the electromagnetic, and we had the gravitational force. Now, of the four fundamental forces, gravity is actually the least strong. It does act over an infinite distance, and it's what's caused the universe to clump together over billions of years, but it is the weakest force that we have of these four fundamentals. Now, as I mentioned in our last lesson, all objects with mass exert gravitational forces upon one another. It's a field, also known as a non-contact force, and as we mentioned last time, it's only an attractive force. So, in order to have the equation for Newton's law of gravitation, and it's called universal gravitation because it is applied across the universe, it's not just locally on Earth or objects orbiting the Earth, we could apply it to an exoplanet orbiting a distant star. So remember last time, we had g, little g, representing either the acceleration due to gravity or the gravitational field strength, and we represented that as g m over r squared. We also had Fg, which we've used in the past, equals mg. If we substitute in for this value of g, what we came up with last time, then we'll actually get g capital M on r squared times little m. So we could put that together as g m on r squared. And that's in fact Newton's universal law of gravitation. G big M little m on r squared. Some versions of this will represent it as F subscript g equals g m1, oh that m went a bit funny, m1 m2 on r squared, and sometimes the g is written at the front. All of these representations mean the same thing. So let's look at what we have. We have g, that's our gravitational constant again. And remember it was that 6.67 by 10 to the negative 11. We've got two masses here. Now, I tend to, if I've got a big mass like the Earth and a smaller mass like the Moon, give big M to represent the Earth, little m to represent the Moon. If we have two masses that are the same, just pick one to be M and little m. But yeah, if the one's bigger and one's smaller, which happens in, I'd say, 95% of our problems, attribute big M to be the big mass and little m to be the little mass. Now, remember, that value of r, that was the distance, but we have to be more specific. It's going to be the distance between the centers of mass, and that's going to be in meters. Our masses need to be in kilograms, and our gravitational constant, we talked about in our last lesson, having interesting units there. So, when we're talking about finding the force due to gravity on two masses, it is absolutely critical that we're looking at the distance from one center of mass to the distance to the other center of mass. So we're looking at this distance here, not the distance from one surface to another, the distance from the center of masses. So, take care. Look at center of mass. Now you'll often find the second object is something so small it's just a point, but if we have two larger objects, keep that in mind. Now, one thing that frequently trips people up, we've talked about the fact that we've got the radii from the center of masses, but we also need to talk about this concept of something called altitude. Altitude is defined as the distance above the surface. So they'll either just directly say the distance of something above the surface, or they'll say the altitude of something. Common question, the altitude of a satellite or a plane or something like that. So the R that we're interested in, the R that we spoke about up here, that's got to be the radius of whatever planet or object we're looking at here. Let's call that R planet. Now that could not be a planet, it could be a star or a moon, but it's going to be whatever big thing we're looking at here. So I'm going to say R planet just for, the purposes of what we're dealing with here. But we need to also add on that altitude. Altitude, there we go, spelled it right in the end. You could write R subscript altitude, but whatever, I've just written it like that. So this, remembering this, is going to get you out of so many problems with these questions here. Also make sure everything has got to be in meters. Frequently we're talking about satellites, which are hundreds of kilometers up, so they often quote those values in kilometers rather than meters. So a few things to keep in mind there just about this distance. From the center of masses, need to look at the total radius, which involves, if we're looking at, as I said, if we have some body here and we've got a satellite, we know this is the altitude. To find that total distance R, we also need to add on our planet. This is the distance R that we care about for our calculations. And we also need to make sure that we've got things in meters, not kilometers. Okay, so we've got a whimsical example here. Rather than looking at very, very large bodies, we're just going to be looking at smaller everyday objects. So let's look at the force of attraction between me, and I'm not going to divulge my mass, but let's just call it 100 kilos. So let's call me Big M. And my dog, who, look, the vet says she should be closer to 20 kilos. She's a little chunkier than that at the moment. And it says our centers of mass are usually no more than, rather than 50 centimeters, 0.50 meters apart. So let's actually go about calculating that force due to gravity using that formula that we just derived before. So remember, G was 6.67 times 10 to the negative 11. The big mass here is 100, the little mass here is 20. Now we're going to say, that vinculum wasn't very nice. Come on. Their centers of mass is usually no more than 0.50 apart. Critical reminder. Remember, we're squaring it. So really, we've got quite a few things we can mess up with that radius. The units, not looking at centers of mass, not looking at the right units, and forgetting to square things. I might have repeated myself there, but hopefully you know what I'm talking about. Okay, let's calculate. Alrighty, so let's get that into scientific notation. And that will be, let's do it to 2 sig figs, 5.3 by 10 to the 7. Sorry, negative 7. That was a very small value, not a very large one. So that is very, very small. We're not going to notice a huge force between me and my dog. Yes, she was named after the Pokemon, and yes, she does tend to do that on my work computer when I'm trying to do things like this. Not going to notice us accelerating towards each other, but it's still a force, and it's still there, and we can still calculate it. So part B says, why does the force on Evie by Miss Black, and that's the magnitude, equal the magnitude of the force of Miss Black on Evie? Well, Miss Black and Evie are two objects exerting forces upon one another. And this constitutes a Newton's third law pair. Therefore, magnitude of forces stated, I should say magnitudes, are the same. So the force of on Evie by Miss Black is equal to the force on Miss Black by Evie. Now, remember, we would just represent that as Fg, like we were doing calculations before. But the important thing to note here is Miss Black, being significantly more massive than Evie, the forces between them both are the same. And again, that's because of Newton's third law pair situation. I will link a video that talks about Newton's third law if you need a little bit of a reminder, because it has been a little while since we've done that. I'll link that in the description of this video. Wow, I sound like a legit YouTuber when I say that. Okay, let's look at some other situations. We're going to look at the force due to gravity on a 70 kilogram physics student. So this is going to be, we're going to be looked by the Earth. So we're going to call the Earth's mass big M, and we'll call the physics student little m. And we're interested first at standing at sea level. Now I know we could just use Fg equals mg, but let's practice using gmm on r squared. We'll put a little note to ourselves. At sea level in future, can just do Fg equals mg, and there g would be 9.8 meters per second squared. That just kind of fit in. When we're on the surface of the Earth, we can use g equals 9.8, no troubles. We're going to be dealing with some situations where they're a little bit further away from the surface of the Earth, and we're practicing using this equation. So we are going to do it the long way, but in future you'd do it the shorter way. So 6.67 by 10 to the negative 11 times, now the big mass of the Earth was told to us here, 5.98 times 10 to the 24 times the mass of the physics student was 70. Now we need to divide by, now it's standing at sea level. So that means that this physics student is standing, we'll say for the purposes of what we're talking about here, on the surface of the Earth. That does not mean their radius is 0, it means their radius is just going to be the radius of Earth in this example. So 6.37 times 10 to the 6, that was in meters, okay, good. And we must square that. Okay, pop that into your calculator, see what you get, and confirm whether you get, let's do it to 2 sig figs. Okay, hopefully you've had a chance to do that. 6.9 times 10 to the 2 newtons. We could do a quick check on our calculator to see if that sort of is reasonable. If we had a 70 kilogram student and they're standing on the surface of the Earth, we could do m times g. And that's pretty close. If we round that to 2 sig figs, we get about the same answer. So that's all good. So same to 2 sig figs even if we did it the other way. So we could have done Fg equals mg, 70 times 9.8, which equals 6.9 times 10 to the 2 newtons, which is the same to 2 sig figs. So that's all fine. But now, this person is at a cruising altitude of a plane, which is about 10 kilometers above the Earth's surface. So, with this example here, we need to adjust what we had before slightly. Still need to write the equation before we substitute, so let's pop that down. We've still got the same g. Oops, let's actually substitute. 6.67 times 10 to the negative 11. And the same masses involved. So just substituting those here. But now that radius has changed. We've got the radius of the Earth that we had before. But now we need to add on 10 kilometers, and that's 10 by 10 to the 3 meters. And that total distance r is the one that we want. You could do a separate calculation on the side of your page here, but I like to actually just do it in here. So this is the radius of the Earth that we had before, and we're adding on that 10 times 10 to the 3. I haven't bothered to write that in proper scientific notation because we don't have to. Okay, popping all that into your calculator, you'll notice to 2 sig figs, you still get 6.9 times 10 to the 2 newtons. We're going to round all of these to 2 sig figs. Do I want to do that for the next one? Yeah, I think so. So that's interesting. Even when we're 10 kilometers above the Earth's surface, our force due to gravity hasn't changed much. And that means if we're sitting on a plane, our experience of how heavy we feel the normal force is going to be equal, if we're traveling at constant velocity, to the force due to gravity. So we're not going to notice a huge reduction in the force due to gravity acting upon us if we're just on a little plane. Let's see how different it is on the space station, however. The altitude, there's that word we mentioned before, is 400 kilometers, or 400 by 10 to the 3 meters. So have a go at substituting in the values for this one, and we'll see if we get any change in that value that we had. Okay, we've started to notice a bit of a reduction in the force due to gravity here. So that would be 6.1 times 10 to the 2 newtons. So even though these astronauts are 400 kilometers up, the force due to gravity acting upon them is not that much reduced. You'll notice that it takes a few hundred kilometers to really start noticing that force due to gravity reducing, but then it begins to drop off quite significantly, and we'll look at the graphs for that in a little bit. So, as a reminder, a person who's on the space station feels like they don't have any force due to gravity acting upon them, sometimes referred to as feeling weightless, because they are not experiencing a normal force. The normal force dictates how heavy we feel, because that tells us how heavily the floor is pushing up on our feet, and that is equal to how much we're pushing down on the floor. And that's how we experience how heavy we feel. Now, a question I've seen on the exam a few times now talks about finding the force due to gravity on us acting on the Earth's core. So a really important thing to note is that this formula, and in fact the formula for G that we had, only works when we are external to a body. So this formula that we had and this formula that we had for G, they do not work when we're within the Earth. So making a note on that on your note sheets would be really, really critical. Don't use the formula for this one. It doesn't apply inside the Earth. We need to use another approach. Imagine we have dug a hole and we are in the center of the Earth. What that means is, as the hole gets deeper and deeper, we are going to be traveling further and further inside of the Earth. Then, once within it, we're going to have mass above us and mass beneath us. We're going to have mass to our right and mass to our left. Mass to our up and right, mass to our down and left. And masses in all directions. What happens here is the force due to gravity, due to all of these, I imagine it's like chunks of masses, but it's really all of the masses above us towards the surface. We're going to have all these forces pointing in opposite directions. And the result is that the sum of the forces of gravity, due to all that mass surrounding us in a sphere, is going to be equal to 0 at the center. So let's have a go at describing why that was so. So the mass surrounds the center, let's say evenly. I put it in quotation marks because the Earth is not a proper sphere, but evenly is relatively good for what we're talking about here. Evenly on all sides. Therefore, forces are balanced. So let's say forces due to gravity are balanced, which results in equilibrium. Now, a way I've seen this question answered incorrectly in the past. Some people try and apply this formula here incorrectly, gm on r squared, and they try and tell us that if r approaches 0, then fg approaches 0. That is downright wrong. in that example, if r approached 0, according to this formula, Fg would actually approach infinity. Oops. Come on, eraser. And that's not the case here. The force due to gravity actually equals 0. If you manage to be able to drill your way to the center of the Earth, not possible for a whole range of reasons. But if that happened and you were able to set yourself up there, you would actually just float there because you would be in equilibrium. And Newton's first law tells us that if the forces upon us are balanced, then we're going to continue doing what we're doing. Now, if you're interested in finding out what would happen if you dug a hole through the Earth and then jumped in, I'll put a link to what happens there because it's actually very interesting what goes on. So, we cannot apply that formula here. It's not relevant beneath the surface. Beneath surface. The reason being, this formula assumes that the entire center of mass of the Earth, it assumes that the entire mass of the Earth is concentrated at the center. But as soon as we start digging a hole, we can't assume that anymore, because the further we dig, the more mass that we have behind us that we've dug through, and the less mass that we have in front of us until we get to the center when we have the same amount of mass behind us as we have in front of us, and left and right, side to side. So that formula is not relevant beneath the surface because it becomes more complicated. We actually have a different mathematical model that applies here. Now, we don't actually talk about the actual maths behind it, but what's really interesting is the force due to gravity graph and the gravitational field strength graph, gets linear. So let's break it down a little bit. So here we've got G. That's the gravitational field strength that we spoke about during our last lesson. And we've graphed it against R. Now, this R here is the radius of the planet that we're looking at. So that's right, R planet equals, they've used capital R here. You'll also notice on the formulae, sometimes they use lowercase r and capital R for these radii, and it doesn't matter which you use in this context. So, you'll notice this portion of the curve here is interesting. You'll notice when we're at a distance of r, we've got this value of g. Now, if we doubled r, it had the effect of quartering the value of g. We spoke about that during our last lesson. It's an inverse square relationship. If we tripled the value of r, that divides g by 9, or it's 1/9 the original value of g. So in this part of the graph, remember g was equal to gm on r squared. So if g is a constant and capital M is a constant, g was proportional to 1 on r squared. Now this other portion of the graph though, this portion, this is when we're within the Earth. Here g does not equal gm on r squared. It's a different relationship entirely, and it in fact is a linear one. Now, I'm not going to talk about the mathematics behind this because it's beyond what you need to know for the course. If you're interested, contact me and I can get you some resources. But you do need to know, if you had to draw in this portion of the graph, that it's linear, and that when r approaches 0, g approaches 0. Now, you'll notice the graph right next to it looks the same. But if I multiplied all of those g values by m, remember that fg equaled m times g. So if I just multiply everything on this side here by m, that means we've actually just given ourselves an fg distance graph. So this is fg distance. All that we've done is multiply by m. It has exactly the same shape because we've got just multiplication by a constant here. So we've got this portion of the graph. That is fg now. And it was gm times m on r squared. So all we've done is multiply an m on the end here to get this. So here, fg is proportional to 1 on r squared. So, like we saw before, when we're at a distance of r, the force on this little mass m was equal to mg, and gs they've got there as the surface. If we double that radius, we quarter the force, and if we triple that radius, I wish it rolled off the tongue a bit better, 1/9, divided the force by 9. Within the Earth, though, this formula does not apply. Here, as r approaches 0, Fg approaches 0. So we spoke about that before. So remember, the curved portions here are when we are above the surface. The linear regions are when we are beneath the surface. This is a hybrid function, you could imagine it as. So very important to know these two distinct areas of the graph. Okay, let's look at some exam questions that talk about doing calculations with this. So, dwarf planet Pluto. In 2007, when I was doing my IB exam, I think that was the year that Pluto was demoted to a dwarf planet. And on my exam, I still had to write that Pluto was one of the planets of the solar system because we had an old study design. That's a cute little detail about life. So if we have some drastic physics discovery that happens before the end of this year, we're going to have to stick to the study design even when the understanding's changed. Okay, so getting distracted. It was thought to be the outermost member of the solar system. It orbits the sun and has a radius of 6 billion kilometers, no biggie. We've got Eris, so that was about Pluto. Eris was discovered, has the same mass as Pluto, that's going to be important I imagine, but the radius is 10.5 billion kilometers, and they've given us the scientific notation there. Okay, so we want to find which is the best estimate of the ratio, gravitational attraction of the sun on Eris. So that's going to be F on Eris, let's write just E by sun, and the gravitational attraction of the sun on Pluto, so force on Pluto by sun. Okay, so the force on Eris by sun, that's going to be G. Let's use capital M to represent, M will be the mass of the sun. Now, little m. I was going to say let's do M Pluto and M Eris, but we said that it was about the same mass, so let's just use that to represent M. So the mass of Pluto equals the mass of Eris. Let's just use little m to represent that. So Gm on. Now, if we're talking about Eris here, we're interested in the radius to Eris squared. Let's also write an equation, F on Pluto by sun. That's going to be G. Big M still the sun. Little m is the mass of Pluto, which we said was the same mass of Eris, m. And that's going to be divided by r, Pluto squared. Okay, so we need to now set up this ratio. I really recommend considering what we're doing here algebraically because it makes life a lot easier. And you'll see in this question they haven't actually told us the mass of the sun. I think that might be something we can look up on our data sheet, but you'll notice for this question we don't need to. And they also haven't given us the mass of Pluto. When that happens, remember, it's probably going to cancel off with a little bit of algebra. So we want to do F on E by S, and we want to divide that by F on P by S. I like to go old school with the division sign when I know that we've got this double-decker fraction action here, as a teacher at our school so famously says. So let's write in on E by S, G M M on R Eris squared divided by G M M on R Pluto squared. Okay, so let's multiply by the reciprocal, G M M on R Eris squared times R Pluto squared on G M M. So now we can cancel off those G's no problem. We can cancel off the mass of the sun, And we can cancel off that unknown mass of each of these dwarf planets. That's pretty good. So all we're left with on the numerator is r Pluto squared on r Eris squared. And that's lucky because that's all the information they give us in the question. So radius of Pluto, 6.0 times 10 to the 12, and we're going to square that. And Eris was 10.5 times 10 to the 12, and we're going to square that. So can I get you to pop that in your calculator and just double check? Because when I did this, I got 0.326 ... and that's going to be closest to our answer of A. Okay, so due to Newton's third law, two objects exert equal and opposite forces on one another. Although the forces are the same, the effect of the force on the two objects can be quite different if they're of different mass. So let's just quickly revisit Newton's second law. Remember, it was telling us that the sum of the forces equals ma, and it tells us that the acceleration of an object produced by a net force is directly proportional to the magnitude of that force, or A is proportional to A is proportional to the net force, like that. And it's in the same direction as the net force, and it's inversely proportional to the mass of the object. Cool. I tend to write it like this, but if we're calculating an acceleration, it's nice to write it like this. But we've done that quite a lot before. So for two objects, perhaps the Earth and the Sun, the magnitude of the force on the Earth by the Sun is equal in magnitude to the force on the Sun by the Earth. Now the thing is though, the effect of this force is different because the masses are different. So however, m Sun, just out of interest, is about, I looked this up before, 333,000 times m Earth. So m Earth, I think it would be safe to say it is much, much less than m Sun. And what that means is the acceleration of the Earth is much, much greater than the acceleration of the Sun. So the force on the Earth by the Sun causes the Earth, which is barely a pixel in this diagram over here, there it is, it causes the Earth to fully rotate around the Sun. The Earth causes the Sun to have an almost indistinguishable wobble due to it. The center of mass of the Earth-Sun system is very much within that Sun. So, although these forces are the same size, the effect, the acceleration, is significantly different. Please remember to keep that in mind. Also remember, Newton's third law pairs do not cancel each other out. If that were true, we would be flying off into space and we wouldn't be gravitationally attracted to the Sun, which is very necessary for our life on Earth. Okay, can I get you to have a go at doing this question here? What I'll do is I'll silently do it. There is some data that we've been provided with, force of gravitational attraction between the Moon and the Earth. We're told the Earth's mass and the Moon's mass, and we want to calculate this ratio here. So using Newton's second law and using some ratios, I'd like you to have a go. If you're not sure where to go with this, can I encourage you to just have a watch here. Before you do that though, and hopefully I haven't lost you, note that the sum of the forces equals ma is not the same as Fg equals mg. Fg equals mg is true whether the object is in equilibrium or not. Whereas the sum of forces equals ma only happens when an object is not in equilibrium. Also, that acceleration is not necessarily the acceleration due to gravity. I mention this because I noticed some people mixing up these two equations here. So just be careful because we are using both in this example here. And if you found yourself confusing these in the past, just watch me do these annotations and see how to go about it. Okay, so apologies, I realised as I was doing that question that I accidentally quoted the moon's mass in meters. It should have said kilograms there. So what we've done here is we've calculated the acceleration of the moon divided by the acceleration of the Earth equals 81. What that actually means is the acceleration of the moon, if we multiply a Earth to both sides, it's going to equal 81 times the acceleration of the Earth. And that's why the moon orbits the Earth, whereas the Earth wiggles a little bit in response to the moon's effect of the force. So that's a really nice way of comparing the acceleration of the moon divided by the acceleration of the Earth being 81. You can think of it as the acceleration of the moon is 81 times the acceleration of the Earth. Okay, looking at this one now. It says the force due to gravity on a space capsule is this value here. It reaches an altitude 3 times the radius of the Earth. We want to calculate the force due to gravity at this altitude. Now, we'll notice we've not been told the mass of the space capsule or the Earth or the radius of the Earth. We could look up some of those values on the formula sheet, but that space capsule's not going to be there, so we need a different approach. We need to consider what the change in the radius has been. So, if the space capsule starts on the surface of the Earth, it is one radius. We could use little r or lowercase r. I'll just use uppercase r, I've already written it. If we then change it to have an altitude 3 times that, let's maybe make this a bit smaller so it's easier to draw. So we'll call that r. If the altitude is 3 times that, we're going to have 1, 2, 3. This distance from the surface here is 3r. But that's not the value that we're interested in. The one that we're interested in is this total distance here. So what we've done is we've changed that value from being r to 4r. So that means that the value of the radius is being multiplied by 4. So therefore, fg needs to be divided by 1 over 4 squared. Oh no. It needs to be divided by 4 squared, or fg is going to be divided by 16. You could also consider it to be fg is going to be 1/16 of what it originally was. So that means the new fg is going to be the old fg, 1.1 by 10 to the 5, divided by 16. When we do that calculation, we get, double check this one, I get 6.9, we'll just do it to 2 sig figs, times 10 to the 3 newtons. So the big one there, recognizing it was 4r we were interested in, because it said the altitude rather than the distance from the center of the Earth. Okay, new one. A satellite on the Earth's surface, it says weighs, that's another way of saying the force due to gravity is 400 newtons. At what distance from the Earth's center will the force due to gravity be 100 newtons? Okay, in this example, the force due to gravity has divided by 4. So doing the opposite of what we did above, that means that the radius needs to be multiplied by the square root of 4. So that's going to be times 2. So that means the radius has got to equal 2 times the radius of Earth. So we're using that inverse square relationship here. Okay, let's finish it up by looking at this exam question. It says we've got the planet Mars and we're told its mass. and it's approximately 1/10 that of Earth, and the radius is approximately half that of Earth. It says, which of the following A to D gives the best value of the acceleration due to gravity at the surface of Mars? Okay, we could do a whole bunch of calculations here, substituting into G equals capital G m on r squared, or we could use these two facts. If the mass is 1/10 of Earth, this is the acceleration due to gravity, so we're looking at G here. So we're tying in things that we did from our last lesson. If the mass is 1/10, we said G was directly proportional to m. So if we divide the mass by 10, G also needs to be divided by 10. And that's in comparison to the gravitational field strength on the surface of Earth. So G needs to be divided by 10. But it also says the radius is approximately half that of Earth. If we halve the radius, that means G, because it's proportional to 1 on r squared, G needs to multiply by 2 squared, which is 4. So that means G is going to be divided by 10, but also multiplied by 4. So we could do 9.8 divided by 10 times by 4, or 9.8 times 4/10, and that's going to give us approximately the value C here. So the inverse square law is something that we've been using in our calculations a bit. I'm going to go through this in class next time because it's really just bringing together what we've been talking about. We use the inverse square law with that past calculation, but talking about why it works as it does is what we'll be focusing on, and that's much easier to do in person. So I've got a couple of explanations that I think you'll find useful for this. It's kind of strange when you first think about it, but hopefully with one of the analogies that I give, it'll make sense. Okay, so you now have the ability to practice the questions associated with the chapter. Let me know if you have any questions. Good luck.